All right, so let's look at the syllabus first. So today is February 16. So missing data analysis. We'll finish missing data analysis today. Then today, assignment one will be out. So I will talk about the assignment one. And then the next class, we'll talk about the dimensionality reduction. So we'll talk about the principal component analysis and then exploratory factor analysis. Then assignment two will be out. Okay. I posted. You can, if you go to the assignment, then you can see assignment one right here, right? So let me talk about. You have three parts. So the part one is about the matrix algebra. So you don't have to calculate by hand. You can use R. Okay. So here is some questions. You need to answer your question, but please copy and paste to your R syntax and your relevant output. Okay. And then this is the part one, and then find the inverse A eigenvalue, eigenvector, and then last part is the using this data set. Um, Please find the regression line using the matrix algebra formula we talked about in the class, right? And then find the regression line using LM function, and then see if they are matching or not. Okay, so it should be very. I mean, the regression itself is very simple. This is a single linear regression. This is part one, and part two is maximum likelihood ratio test. So you need to download this part2.csv file, okay? And then there are two variables. First one is teacher's effectiveness and achievement test score and teacher's effectiveness. So you need to run single linear regression analysis using LLME package. So you can see the example from my R code, and then what is deviance, and you need to answer these questions. Okay, so we'll do AIC, BIC values differ between two models, or blah blah blah. And then this is part two, and part three is about the missing data analysis. So this data file is from uh, this one. Okay, exactly same data, but I deleted some values. NA means missing. Okay, so here is so your organization is looking to hire employers for a job where cognitive ability is highly important. Cognitive ability test scores, the 70 was used as a cutoff score. So if their cognitive ability score is less than 70, they were screened out, so their values are missing. Okay, and then first, import your data into our program. Second, list rows do not have missing values. List rows do not have one or missing values. Then plot and evaluate missing pattern. And the third, last one is you need to run regression analysis using mean imputation approach, and then stochastic regression approach we'll learn today, and then multiple imputation approach. Okay, and then report to your results and compare your results to describe how how does your result are different. Then this is the last question. First, you need to read this assigned paper. So I posted it. So this is the paper. This is the annual review of psychology, 2007 or something. I think this paper is a really good summary paper. So missing data analysis. Please read this paper first, okay? And then you can answer these two questions. Compare and contrast the three missing data mechanism, and briefly describe consequences of each mechanism, and describe three steps of a multiple imputation method. Then briefly discuss the advantages of MI method over traditional old methods. Okay. So you have a 1 week. If you have any questions about homework, so feel free to email me. Or if you want to have individual meeting, so I can set up an individual meeting with you. Okay. So any questions about homework? No, it's good. All right, sounds good. So let's finish missing data. Okay, so in the last class that we talked about the missing data, we talked about 3 different mechanisms of missing, right? So first, missing completely at random, and missing at random, and missing not at random, right? So missing completely at random this is totally random. So right, it's like the flipping a coin. So M represents the missing data. So our missing data is not related to our variable. Okay, this M missing is totally random. It only influenced by some third factor, which is from some test takers. Okay, so this is missing completely at random. We talked about it. And then missing not at random is our missing value, missing data is systematically related to observed data, right? So this is missing at random, and then missing not at random is our missing is related to the missing variable itself. So in practice, it is almost impossible to know the source of missing not at random. So we just treat the missing values as mcar or mnar. Okay, so this is what we talked in the last class. And then how can we deal with the missing, right? So first we can remove the missing values, list-wise deletion. So pairwise deletion. So pairwise deletion is very commonly used for the correlation analysis, right? So, but those methods are assumed that your data, missing data is missing completely at random. So if that assumption is violated, your statistical power will be biased, or your primary will be also biased. Okay, so list-wise deletion, we talked about it, pairwise deletion, and we talked about the patterns, right? So now we'll talk about a single imputation method. All right, so before we go there, I will, this is what we talked in the last class. Missing. Okay. Okay, mean imputation. All right. So single imputation method. So the single imputation method is just to simply replace your missing value with some single number, right? So this is, I mean, traditionally, this is most commonly used method to deal with the missing. So you can impute the mean, or you can impute the median values, right? So, but this, the upside is you can still use, unlike deletion method, you can still use the entire data set because you replace any missing value with the mean or median, right? So you don't need to worry about losing power. So that's a good thing. But downside, it still produces the biased primary estimates and also standard errors. So if you impute any values, any missing values with the mean or median, right? Center of the distribution. So that imputation reduces the variability of the data, right? So mean imputation will attenuate the standard error or standard deviation and variance. So restricting the variability of the data also attenuate the magnitude of correlation or covariance. So these methods almost always produce the biased estimate and standard errors. Okay, even if missing is the M car. Okay, so it has a pretty serious type 1 error issues. So in practice, please don't use these techniques. This is bad. Okay, so single imputation method. So look at this. This is the original data set. So this is IQ score, and this is job performance. Okay, and let's say we have some missing. These data are missing. Okay, so we do not have this data here. But if you impute the mean, right? We find the mean and impute all the values here, right? So your distribution of your data becomes homogeneous and the variability will be reduced, right? This is the original data distribution, but this is new data distribution, right? So this caused a lot of problem in estimation wise. Okay, so we'll see the here. So list-wise single imputation. Okay, so you can do the single imputation using the HMISC MISC package. So this is for the single imputation. So if you load it, and then if you want to imputate, so you can just use the impute function. Impute, and this is variable, and no, I'm sorry, it's a data. Okay, so this case is this is mcar, and then I'm going to use mean imputation. Okay, and then I run it and I save it. So if I run it, error, what's wrong? This one. Did I? Okay. And then, uh-oh. Must apply. What is the problem here? Right. Oh, what's wrong here? What's data frame? This is weird. Okay, let me, I will fix this one later. So give me a second. Okay, so this is for impute, so function. And then this is mean imputation. So I'm not sure why this has some issue here. Compute, right, mcar, this is correct. And library, this is correct. It's weird. Okay, I will fix this one. So the idea is, so we can use the impute function, and then this is data set, and then this is mean imputation. If you run it, imputed data will be saved here. Okay, so it's a simple. So it's impute another data set, mean imputation. And if you want to do the median imputation, you can type median like this. Okay. Okay, and then, yeah. Oh. Okay, so then you can also compare to your mean, right? I created some the character vector, the complete mcar, mar, and nar. Okay, and then I get the mean from the complete data set, mean from the impute mar, mean from the impute mar, and mean from the impute mnar. So I get the mean, and then I just compare the mean here. So this is a complete data set mean, right? And then our mcar, so mcar data, so missing complete at random is pretty close to the complete data set mean. And missing at random is still close to our complete data, but missing not at random is it is kind of biased, right? So you can see almost a 1.0 difference can occur. So if you want to check a mean from multiple approach, you can use this approach. Okay. So then same here. So we can check this is a standard deviation of the complete data set, and then missing completely at random and missing at random. So missing complete at random, missing at random. So our standard deviation after imputing the data, the standard deviation is still pretty close to this one, but missing that at random is the biased estimate. Okay. Okay, so now we will talk about the regression imputation method. So regression imputation method is so it replaces missing values with the predicted scores from regression equation. Okay, so first step of the imputation process is to estimate a set of regression equations that predict incomplete variables from the complete variables. Using the complete variables, we derive some regression line. Okay, and then we predict missing value using that regression line. So the second step is to generate the predicted value for the incomplete variables. So step one, we derive the regression line using only complete data set, and find the regression line, and then predict missing value using that regression line. Okay, so that is the regression imputation, so which is also called conditional mean imputation. So for example, this is our data set, right? But let's say we have these are missing, right? We do not have missing, we do not have this variable. So try to find the regression line using the complete data set. Okay, this is complete data set, and find the regression line, right? So this will be the regression line, right? That these are all the missing values, right? And then we try to predict using this regression line. And our missing values will be like this. Okay. So the imputed missing value will be only always on the predicted regression line here. Okay. But do you see any problems in this approach?
Well, I mean, let's say part of the distribution, like if all of the like range restriction, all the missing values are maybe at the lower end of the.
Yeah. So look at this. So what is the basic assumption? What is the fundamental assumption of regression analysis? Homoscedasticity, right? So we assume that the variables, the data points, has this equal the variance. But in this case, they are all the same. They are all on the same regression line. There is no variation. There is no error here, right? So error portion, error is ignored. So it restricts the variability of your data distribution. So it will reduce standard error. So it will affect the power. and then it produced a biased estimate. Okay, so another approach to deal with this problem is stochastic regression imputation. So stochastic regression imputation, it still uses regression imputation to predict incomplete variables from the complete data, but it takes error portion. It take account the residual part. Okay, so from the normally distributed residual term. So adding residual to imputed value restores lost variability. So in the regression imputation, we'll lose some variability, right? But the stochastic regression imputation, it restores or lost the variability to the data. So here is an example. So like I said, this is missing, right? This part is missing. So we find regression line using the complete data set, right? And then this is our regression line, right? And regression approach, we just impute all the values on this regression line. But stochastic regression imputation is, it assumes it has some normal residual distribution. And then we randomly sampled error values from each distribution and add it. Okay, so this value was here in the regression imputation, but now it includes some error. So now it is here, and here, here, here. So in this way, we can make some variation, and we still keep the equal variance assumption. Okay. So do you follow me here?
Is the distribution parameters that the error term comes from, is that only based on the observed data?
I'm sorry, so I don't hear you clearly.
Like the distribution, the normal distribution that the error terms are taken from?
Error terms.
Are they only based on the observed data? Or if you impute a new, does that get added into?
No, that distribution is from this regression line.
Okay.
Okay, so using the complete data, we find the regression line, and then we assume this regression line has some distribution, right? Normal distribution. So we randomly sample the error values from that normal distribution and then add it. Okay. So this is stochastic regression imputation. This stochastic regression imputation is used for multiple imputation method. Okay. So before we go there, I will run. This is a stochastic. So okay, so this is just I'm not before we there. This is deterministic regression imputation. So this is just regression imputation. Okay, using the mice package. This is our data, right? MCAR. I created the MCAR data, and then in the method, normal predict. So we're gonna predict some value from this. The function is for the regression, deterministic. And then if you run it, and you can see, it is run iteration imputation variable, and then you can get a complete data set using complete function. If you run this one, and then now let's print out. Okay, so now we have a complete data set. All these values are imputed based on the regression without error term. Okay, do the same thing for the MAR and MAR. Okay, This is a regression. And then you can run any analysis using this imputed data, okay? And then this is a stochastic regression imputation. So it's still, you can still use a mice package, but the method here, norm.nob, okay? This is for the stochastic regression. So if you run it, and then this is complete data set, run it, and then now we can check your complete data set. Okay, yep, now we impute. So these values are all imputed. But this imputed value had some error term. Okay, so this is for stochastic regression imputation, and also you can do the same thing for the MAR data and NAR data. So I will just run. Okay, so if you run mice package, okay, so mice package multivariate imputation by chain equations. So it was method, right? If you go to method, so you can see many different options here. Where is method here? Right here. So norm, Bayesian linear regression. You can try many different methods. Linear regression and random indicator logistic regression, Polytomous logistic regression, and like this. So if your data, if your missing data is continuous, so definitely you can just use a linear regression, right? But if your data is dichotomous or categorical, in that case, you need to use logistic regression instead, right? Does that make sense? Yeah. So you can check. Please check this one. So a lot of different built-in methods here. Okay, so and then now I will show you the graph. So please don't focus on the coding here. So just focus on the graph. So I will plot it. So this is our regression imputation first, right? And then this is the regression imputation. So I plot the regression line, right? And then we plot the missing value. So all the missing values are on the regression line. But if I do the stochastic regression imputation, so this is a regression line, regression, and then I added the regression line, but I was missing values. So they're all here different, right? So this missing value is, the error term is sampled from the normal distribution that they added. Okay. So any questions?
I have a quick question here.
Mhm.
Before we conducting the regression imputation, are we assuming that the dependent variable and the independent variable have a linear relationship?
Mm-hmm.
So if we assume they don't have a linear relationship, like there is a U shape between IV and DV, we can't use regression imputation, right?
Correct.
Okay.
So if your data, I mean, the linear imputation method assumes that your regression follows a linear assumption, right? So if you have, for example, non-normal data, or sometimes if you have some non-linear relationship, in that case, the linear relationship will not be work. So in that case, maximum likelihood estimation is the solution. Okay, so yeah. And any other questions? Nope. Okay, so why single imputation is bad, right? So overall, the methods described here are not useful for handling missing data, right? So if you use them, you will have some artificial effect in your statistical analysis, right? So the estimates will be biased because your distribution of your data set will be restricted. Okay, so distribution of your data set is restricted, so it will affect the standard error. The standard error will affect your t-test, right? So it will affect your power. So you will have a lot of type 1 error. Or overinflated, underinflated, right? So it leads to the type 1 errors, right? So you will likely end up making conclusions about your data that are wrong. So the single imputation is bad. So don't use deletion method or single imputation. Okay. So in your question, the question part 3 asks you to run 3 different approach missing data. The mean imputation, stochastic imputation, and multiple imputation. You will see how mean imputation destroy the true relationship of your data. Okay. Right. Next, multiple imputation. Rather than using a single imputation, so the better idea is to use multiple imputation, right? So we make a multiple complete data set with the plausible, the missing values. Okay. So it will help us to get unbiased estimate and also unbiased standard error estimate. Okay. So multiple imputation is mechanisms by which you fill in your missing data with the plausible value. So the multiple imputation is an extension of stochastic regression analysis, stochastic regression imputation. Okay. So it also assumes your observed data follows multivariate normal. So which means that your error term has equal variance, right? So your error, residual errors has normal distributions for all the data set, all variable. So multiple imputation consists of 3 different steps. So step 1, the missing data are filled in a number of times to generate m complete data set. So we generate multiple data set with replacing missing with plausible value. Okay. And then step 2, so an m complete data sets are analyzed using some statistical analysis. And then step 3, that the results from the m complete data sets all combined, aggregate. So let me turn off my. Okay, so first step is called imputation stage. The second step is called analysis stage. The third step is called pooling stage. Okay, so this part is imputation stage, and this part is analysis stage, and this part is pooling stage. Okay, so let me explain it. Oops. Let's say we have X, Y, and Z, 3 variables, and we have some missings for X, Y, and Z, okay? So in the first, using the complete data set, complete cases of X, Y, Z. Okay. Do we use only complete case? And then we predict X equals Y plus Z plus some error. Okay. And we predict Y value and we replace the missing with this predicted value and then make one complete data. Okay. And do the same thing for Y, X plus Z plus E. And then we predict Y. And now we predict Y. And then do the same thing with the X plus Y plus E error equals Z. And we predict Z. Right? So because we added error term, every time we run this analysis, our results will be a little bit different, right? Because of this error term. So we repeat this process n times. Okay, you can repeat 10 times, 20 times, and 100 times. Okay, and then repeat it, and then you will find the last set of data, right? X, Y, Z. That is our complete data set. That is data one. Okay, so let's say we created 5 different data sets from this missing. Okay, and then we go through this process again, and then create the second missing data set, complete data set, and do it again, and third, and fourth, and fifth. Okay, so in this case, M is our data set, complete data set. So in this example, I just created a 5 complete data set, but you can create the 10 data set or 20 data set. Okay, so rule of thumb, the 5 to 10 is enough. It's okay, but sometimes it depends on the proportion of your missingness. If you have a lot of missing, in that case, you need to increase the complete data set, number of complete data set. Okay. Again, this process is what? This is a stochastic regression, right? So this imputation process is called repetitive stochastic regression process. Okay. So this is imputation stage. We can do this stage using mice function. In R, mice function will do this for you. Okay. And then next step is statistical step. I'm sorry, the analysis stage. So now we have 5 complete data set, right? So we will run regression here in this example. We will run regression. So we have intercept and slope, right? From the first data set, and then from the second data set, we run it again. We will have another intercept and slope, and run it again. We have another intercept and slope, and run it again. So we have 5 sets of parameters in this case. So this is analysis step, and then pooling step. We can do this with the width function. Okay. And last step is pooling stage. So pooling stage is we aggregate the different parameters. We just get the sum. Okay. The standard error is a little bit complicated, but they use a different formula to get the aggregated number. But any main idea is we aggregate all different sets of parameter and get the one number. Okay, So this is the multiple imputations. Questions?
Phil, I have a question.
Sure.
Beyond like information loss,
Where?
so like once you get to the analysis stage,
Mm-hmm.
why is it frowned? I mean, it makes sense, but why is it frowned upon to not just aggregate all the complete data sets and then run the analysis one time instead of pulling the analysis, each analysis? Does that make sense?
No, I don't understand.
So you see the imputed data sets.
Yeah, we have a 5 imputed data set.
So then
here.
if you like run complete, then go to one data set.
Yeah, we use this one.
And then you just run instead of running the analysis 5 times,
Mm-hmm.
you run it just once. Does that make sense?
I mean, we have a 5 different data set, right? It's complete
Yeah.
data set. So each data set will be used for the regression analysis,
Okay.
right? And so what you're saying is why don't we aggregate this variable?
Well, I'm saying like, what are the concerns if we do aggregate the 5 data sets and then just run one regression? Aggregated.
No, I mean, if you do that, we still may have some the bias.
Yeah.
So by doing this, we'll try to reduce any possible biases by running multiple times, the 100 times, 200 times, right? So sometimes your estimate could be overestimated. Sometimes your estimate will be underestimated. If we get the average, but our assumption is that it will be close to the true parameter.
Okay.
Okay. And also, by doing that, we can have some distribution of parameters. Okay. So do you all clear here? So ask me a question if you're not clear.
One more question. The only difference between the first imputation and second imputation is they have different error value. They have different errors.
Yeah, different errors. No, I mean, yeah, different errors.
Okay.
Yeah.
And that error is from a distribution we set.
Correct.
Okay.
That error is the distribution of the parameter set. And then we assume that that error follows the normal distribution, right? So -3 to +3, for example. So sometimes you could sample from here, another time you could sample from here, So by increasing number of repetition, right, we can get more the unbiased estimates. Okay. So again, let me summarize. So the multiple imputation steps, they had the 3 steps. The step 1 is imputation step. The basically imputation step is based on repetitive stochastic regression, right? We predict missing value based on the regression model, adding error term. And then we update our missing value, right? And then we get and then we repeat this process over and over and over again. And then finally, we will get the final set of parameters. Okay. So, and then once we get the complete data set, and then we run each analysis, and then we aggregate all the results. Okay. Any other questions? You're good? Okay, so R has 2 well-known packages for multiple imputation. So first one is a MICE package. So MICE is multiple imputation by chained equations. The second one is Amelia package, and MI with the MC assuming multivariate the normal assumption. So, but this class, so I will use a mice package. So, and also there are a couple of other the packages, so allowing you to compute the multiple imputation in R. But mice package, I think, the one of the most the popular package to deal with the multiple imputation. Okay. So here is some code. Let me share my screen. Not screen. So this is okay. I will. So this is a step 1. Okay. Step 1, and I use the mice function, and this is my data set. And then M represents the number of the data set, complete data set. Okay, so I will create the 20 data set. And the method actually default is mean. This is predictive mean matching. So this is default. So you don't need to enter this one, but I just put here method is mean matching. And then this is maximum iteration. So I will repeat imputation stage 100 times. Okay. And then I put diagnostic equals true. So it will give us some diagnostic statistics. If you run this one, so now you can see here, right? This imputation is repeated the 100 times and 20 data set, right? So these are all the different data set, and these are the replication, okay? And then now we can get, we can do the analysis stage using with function. This is data set, and then you can enter your model, statistical model. But thing is, the mice function, mice package is generally available for the general linear model. Okay, if you want to run some latent variable modeling like a CFA or structural equation modeling or multi-level modeling, so Lavaan package can deal with all those the latent variable modeling, but you can still use a mice function for Lavaan. So I will show you later. Okay, but in this case, I just run a single linear regression and then get the summary. So as you can see, right? So the first set of intercept and IQ slope, and then this is the results from the second set of data set, and third set of data set, and fourth set, the fifth, the 1, 2, 3, 4, fourth set of data set, right? So we can have a little bit different intercept and slope values here, right? So and then last stage, the we pool will aggregate all the results, the using pool. So run pool and then get the summary. So this is average the results. So term intercept is a minus 2.14. This is average of intercept from the 20 different analysis. Okay, and this is IQ. This is average of intercept and standard error. And then now we can see p-value and right here. So IQ is significant predictor of job performance in our case. And then the slope is 0.12. Okay, so, and this is how you can find your complete data set. So we have 20 data set, right? So using complete function, okay, I want to get the first set of complete data set. So run it. So this is the first set of complete data set. So all the missing values are imputed here, okay? And what about the second case, second data set? This is the second data set, right? So we imputed 20, right? So 20, right, the last set. Okay, in this way, you can get the computed, complete data set. Okay. Questions? No? So here, oops. Okay, so once you run mice, and so this is then once you impute your data and then you will run your analysis, that is analysis phase. So for example, it could be 100 times, 200 times, right? So in this case, my model is really simple. I have only 20 data points. That's why it took pretty quickly. But if you have the large data set and if your model is pretty complex, it will take a lot of time, okay? So you should be careful with that, okay? And then compile all the results. So mice will automatically do this for you. Okay. So and then pooling phase, in the pooling phase, the results are pooled and report, right? So for primary estimates, the pooling is straightforward, just to get the average primary value across all imputed data values. Okay. So and then yeah,
Well, I have a question.
sure.
So for the pooled estimates, the degrees of freedom, I noticed were like had decimals. Do you know where those are coming from?
Definitely, it will use the mathematical function,
Okay.
but I'm not sure.
And like the model pool.
Yeah. So, and then you can evaluate this is plot function. Using the plot function, you can evaluate convergence. It will show you all the different trajectories across the iterations, okay? I run 100 times, right? So it will give us, okay, first, when the first iteration from here, and second iteration here, third iteration here. So across the 20 data point, 20 data set. So if these trends falls in a certain range, so we say, okay, this is converged. Okay, so they're all between, between 8 to 10, right? So that is evidence of this stable, the estimation. But sometimes you may see these kind of the weird patterns, right? Some looks like this. It's like the U shape or something like inverted U shape. Okay, so that is this is one diagnostic picture, and then second, this is a strip plot. So it will give us, so this is a complete data set from IQ, and then the MAR, this is imputed data. So all the blue dot represents the observed data set, and then a red dot represents imputed missing value. Okay, so we want our imputed missing values that falls in the range of the observed data set, right? So the red dots, they are all falls in the observed data range, right? If we find some missing the red dot, like, okay, here's a red dot over 16, okay, so 20, whereas the red dot is here, so that means our missing imputed missing, predicted missing is out of a range of our observed data set. Okay. This is another way to evaluate the convergence of your missing. Okay.
I have a question. Is this just like in like practicality, like just kind of like a Bayesian process where you just have some type of like prior information being your complete data set, and then you're just using like MCMC chains and stuff like that, like iterations to find that like missing value? I know it's probably not like exactly the same, but is that kind of
Yeah.
Okay.
Yeah, I mean, like I showed you, I mean, you can, do you mean the Bayesian missing, the Bayesian imputation?
Yeah, it just, you know, the a lot of like the plot that you were showing earlier, the I forget what's called, but it just like
Like
brought me
this?
back to it brought me back to like the Bayesian stuff that I've learned. And I was just wondering if like semantically, is it just kind of similar to?
Yeah, it's kind of similar.
Okay.
It's a similar. Yeah. It's a similar pattern. Okay. So if show, so actually, this is really big. I mean, if I run only 3 and 10, yeah, right here. So it will show us. So I just created 3 different sets of data, complete data set, right? So we have 3 different lines, and the x-axis is number of iteration. Okay, so 1, 2, 3, 4, 5. So how many? Run it. Did I run 20? 10, yeah, 10. So this is 10. So 10. So this is the first imputation, the first complete data set is imputation first here and here, here, here. So this is mean of imputation. Okay. So, and then this is the second set of data, the third set of data. Okay. So we want these patterns are pretty stable and within certain range. But if you have like, you know, very irregular patterns, that means there is something wrong in the predicted mean matching approach. Okay, so this is, yeah. And then now I will show you. So, I mean, the mice package generally works for the general linear model. So sometimes you want to use a mice package mean imputation for another analysis, right? So like the latent class analysis or conformity factor analysis, the EFA, multi-level. So you can use Lavant package. Lavant package, they're very powerful. So how can we do that? So first, you can build model through the Lavant, right? This is the CFA, let's say this is the CFA model. And then run MI, this is a function. And then specify your data set, and then specify the number of completed data, and then MI package mice. That's it. Okay, and then specify function, mean structure is equal, and if you run it, you will get the result based on the MI package. Okay, so imputation and model estimation will run at one time. And also this is the second. Also, you can use the full information maximum likelihood estimation. It's much easier. So you can simply add missing equals full information maximum likelihood estimation. So full information maximum likelihood estimation is basically it's a maximum likelihood estimation. It takes a little bit different approach compared to the multiple mean imputation. So multiple mean imputation samples create a lot of complete data set, right? So it is playing with the sample. But maximum likelihood estimation is playing with the parameter. It's a little bit different. So it doesn't do the sampling process. So it starts from any random initial value and try to find the maximum, like any possible parameter of missing data having maximum likelihood. So different approach. So multiple imputation is playing with the sample, but maximum likelihood estimation is playing with the parameter. Okay, so if we iterate many different times, we can get some posterior distribution of parameters, okay? And then try to find maximum likelihood of this primary distribution and then find it, okay? So this is beyond the scope of this class, but so this is the main difference between the MI and then full information maximum likelihood estimation. And then if you're looking to go deeper, so I highly recommend this textbook. This is a great textbook. I love this textbook. So Applied Missing Data Analysis. So this is really good. He describes beautifully about maximum likelihood estimation or some missing data and generally multivariate statistics. Okay, so if you're interested, please read this book. And then this is some the map. So first, you can identify missing values using is.na function, right? Or exclamation and complete dot the cases. These are all, right? So using these, so you can identify your missing, and then you can you can decide, are you gonna delete? So if you, for example, you have a very small missing values, so it will not affect your distribution. In that case, you can simply delete, right? You have a 10,000 data points, but only 1 or 2 are missing. In that case, I would delete, right? So how can we delete? Use omit.na in R. Or if you run correlation, it will be pairwise, right? And then also you can run the maximum likelihood estimations. The most package includes the full information maximum likelihood estimation, but MVMLE package is for compute the maximum likelihood missing value. And also single imputation, HMISC package, and multiple imputation. We just talked about the MICE package. Amelia package is also very popular, and the other packages are available. Okay. Okay, so this is for today. Do you have any questions about missing data? No. So I will go back to the homework one more time. So this is the homework 4, the question part 3. So here are the missing, right? And then you can easily do this one. All the example codes in my R code, and then run regression using mean imputation approach. Run regression model using stochastic regression approach, and then multiple imputation approach. And then when you run this one, please just set m equals 50 and maximum equals 50, and then add the seed number. So look at here, like seed equals 1, 2, 3, like this. Okay. So by adding seed number, your values and my values will be matches. Okay. If you don't put seed numbers, your number and my numbers will be different. So for the grading purpose, please add the seed number in the mice. Okay. Seed equals 1, 2, 3. And then compare these 3 results with the this full regression analysis from the full data. Okay. And you will see how different the missing approach yields biased estimate. Okay. All right, so any questions?
I have one more.
Yeah.
talk more about the iterations in each imputation? I'm not very clear why do we have iterations in each imputation? Isn't that something like a maximum likelihood process?
I'm not very clear.
Or could you explain more about the max iteration?
Yeah, sure.
Yeah.
So so for example, so X, Y, and Z, right?
Oh, you're not sharing your screen right now.
Oh. I didn't share my screen. Okay. Now you're good?
Yeah, good.
Okay. So X, Y, Z, let's say we have three, the missing. Okay.
Mhm.
So first, using the mean, using complete data, right? So we X will be predicted using Y and Z plus error,
Mhm.
right? So we predicted X, and the Y equals X plus Z. So we predicted Y, and then Z equals X plus Y plus E, and so we predicted Z, right? These are the complete cases, right?
Yes.
Cases. So then we are using this complete data set and predict again.
Predict again.
Yeah, predict again.
That's all happens in one imputation.
Yeah. So and not yet. So okay. So we predict again, right? And then if we predict, and then we will get another X predicted variable, right?
Yes.
So and then another Y variable,
Uh-huh.
Y data, another Z data, right?
Uh-huh.
And we update it.
Oh.
Update it, and then repeat it again.
Oh, I got it.
And then get another, and this is the first iteration, second iteration, third iteration, and to the 20. So this will be the updated last missing value. So this is a complete data set.
Okay.
Okay. If we reiterate many times, these changes will be very minimal, negligible.
Yeah.
Right?
Yes.
So we repeat this one.
Okay, I got it. Thank you.
You guys okay? You guys follow? Let's do one more time. So let me explain one more time. Okay. Yeah, I know this is a little bit complicated process. Okay, so we have three initial the data, and they have a missing. First, we predict X, right? And then Y, and then Z. By adding error, every time we estimate, we will have the different numbers, different data, different predicted mean. And then we use this complete data here, update, and estimate X again. I will say 1 and 2. Okay, do the same thing, estimate, and estimate. And we update and repeat again through the iteration process. And then X3, Y3, and Z3. Okay, and then plug this one again. So we will get another data. If we do the 20 replication, we'll have 20 times, and then we'll have last set of data, right? So let's say 20, Y20, Z20. So this last set of data is first complete data set. Okay. And for the second complete data set, we do this process again and make a second complete data set. And do this process again, and third, and do this process again, and fourth, and fifth, and then stop. In that way, we can create the 5 different set of data set, complete data set, and then run regression or run any analysis, and pull all the primaries together. Okay. Questions? So does this make sense to you? Okay, so
Yes, thank you.
all right, okay. So if you don't have any questions, I will stop here. Okay, so I think it's time's up. So do you have a 1 week for your homework? So if you have any questions, please let me know. I'm willing to help. Okay, all right. I will see you on Thursday. Okay, bye.